So here's the agenda for today. We'll talk about what is hardware, and then we will go to its main components. Then we will talk about the TySOM and VSOC development work, and something about using the VUnit pre-config and post-check functions. Then we will jump to the debugger project and Aldec IP USB bridge that is new to us in this example. Then we will go to the HIL example flow and also know something about the Riviera-PRO and its advanced debugging and testing features. Then I will jump to the demo section and present the key benefits of this flow, some potential use cases, and wrap up everything with conclusions. And then there will be a Q&A session. Okay, so let's start. What is the hardware in the loop? Hardware in the loop is a real-time testing technique where a physical hardware component is connected to a simulated environment, represents the rest of the system. And hardware in the loop allows early validation of the project because it replaces parts of the system with simulation or software models. So we started this project from the simulation and software models only, and then we added some hardware, and this is how it goes. So in HIL, the hardware interacts with these models, the software and simulation models, as if we're operating in the real world. So it means receiving inputs, producing output, and running in real time. This approach makes it possible to test safely, efficiently, and under a wide range of scenarios, including the fault one, without the risk of cost of using the actual complete system. The main components of HIL in this project is, of course, VUnit. VUnit orchestrates test execution and integrates all other components. A single script, runtime script, is responsible to run everything. A TySOM MPSAC board, this is the hardware part, and it performs decryption because the demo will show AES encryption and decryption. So the TySOM is taking decryption entirely in programmable logic, so we have acceleration here because we don't need the processor involvement. And the third one is Riviera-PRO. It provides advanced debugging and verification features and simulates the whole flow, including also the data flow from the hardware, from the host to the PL, and in opposite way. So this is the TySOM VSOC development board and its technical specification. TySOM is used in prototyping software, hardware simulation stuff, and so on. It's used widely by engineering. The most important part of this TySOM today, I'm gonna show how we use the FMC connector. We have two connectors like here and one up there. So we utilize one of them to plug some FMC adapter board. And we use also a PL side of this board. The next slide shows us FMC adapter board that we use in this project, and it also has FMC connector, which is plugged in the TySOM board. And the board excludes the TySOM connectivities and enhance its usability. So in this demo, it serves as like a USB bridge from the host to the PL side. Okay, next topic is using VUnit pre-config and post-check functions. As you well know, I bet, pre-config cryptographic function is the function before the test and simulation start. So it's going as the first function. And in this example, it prepares input data for the encryption process, so the key and the plain text, and it stores them into a file. Next, the post-check function. It comes into play after the simulation ends, so a bit later. And it is responsible for the data communication. It is responsible for sending the data to the TySOM and receiving it back from the TySOM. TySOM is our hardware. Something I didn't mention? I don't think so. We also use some other functions from VUnit, like check wall and so on, but I will explain it later. This is the Vivado project, so something for the hardware engineers. This project is put into the programmable logic of the TySOM. It consists of mainly of the RTL blocks that Aldec writes, and the flow is from the left to the right side. On the left side, we've got 3 lines that are responsible for giving us the data that we need for the decryption process. And from there, we've got also a synchronous FIFO. The FIFO is for making synchronization and well timing. And from the FIFO, the data is going to the special blocks like AXI-S Packer. The Packer is used to complete the 32 bits of data. It's a one transfer to 4 of the transfer to get 128 bits data. And the same for the key. So the plain text and the key should be like this. After the packing stuff, we also have our main RTL module. This is the AES deck. It's about the decryption. So it's doing the part of the decryption. And from there, it's going to our top model. The top model is USB bridge Aldec IP, and it's written also by Aldec in RTL. So it orchestrates the communication between the host and the PL, and it's receiving the data, and after everything is done on the PL side, it's sending it back to the host. Something about Aldec IP USB bridge. So the main function of Aldec USB bridge is managing the communication, as I was said earlier, over the USB between host and TySOM board. It's a synthesizable USB IP implementation that we use in the TySOM board. And the data format of a single transaction is as follows. The first is operation, so the write or read. Then it goes size, so how much data we need to send. Then the address and the actual data. So here's the diagram that shows what exactly is going on the host and what exactly is executing in the TySOM PL that involves the bridge usage. So on the host, inside the post-check function, we send data for the decryption to the TySOM PL. TySOM PL waits for the data, and once it receives it, it's making a decryption and write the results to the register. And host waits for the end of the decryption process and read data from this register. So this is the example flow scheme. As we know its components, we can now show the whole. On the left side, there's a host PC. It's our one part of the design. And on the right side, there's a TySOM PL. This is the second part of the design. To run everything on host, you need VUnit, Python packages, and Riviera-PRO. And the flow is starting from the left upper corner. We see that the text file with plain text and key in hex format, hexadecimal format, is generated in the VUnit preconfig function. And from there, the simulation is taking care of reading the data. And inside the test bench, the data is encrypted. And after the encryption process, the check equal function is called to check if the encryption process was good. When everything is okay, the results are written to the text file. Next, the text file in the postcheck function is passed to the TySOM PL. It is parted into some data, smaller packages, and sent over the USB cable. First, the data is going to the USB bridge Aldec IP, and from there it is going to the synchronous FIFO. From there to the AES decryption, where the decryption is taking part. And after the decryption, it is stored into the register. And to receive the data back, it should go to the opposite way it comes to the TySOM. So first synchronous FIFO, and then USB bridge Aldec IP. And from there, it's going to the USB cable to the host again. Why so that? Because we need to compare if the generated plain text and key in the preconfig functions match the data, so the plain text after the decryption. And we do it in Riviera-PRO and also simulate the whole flow. About Riviera-PRO, I bring to you I choose two features of it. The X-trace, maybe you heard about it. The X-trace tell you where to find the bugs that are unknown states of signals. So as you can see, we can discover the bugs when the cipher text or the plain text have some unknown values, and the X-trace will show where to find them and maybe how to fix them. The second of the feature is a test plan. It's coverage-based tests. In this example, I will show you some coverage tests. It includes the statement coverage, branch coverage, condition toggle, and path coverage. So here are the example results of the coverage that we achieve running the 10 tests. We will do so in the demo section, so I will give you a taste. And the ranking results also are very useful way to detect if the code was coverage or no. And each next test gives us some coverage increment. And after the whole tests, there is a sum up. We actually get the 90% of coverage after 10 tests. Okay, so it's demo time. I've got a TySOM board here with me and FMC card also. It's plugged into my laptop through USB cable. Oh, sorry. Oh. just run 10 tests. It will be Python run by dash n. Maybe I will enlarge it a little bit. Dash n is an option that I added to the VUnit parser to run specific number of tests. As you can see, the tests are going. One test is taking about 2 seconds. It depends on the resources that you have on your PC, like RAM or processor. In the Riviera-PRO, the tests are made to get the coverage, and we've got some records from the X-rays. The X-rays found a bug, and if we look closely, it tells us that the bug is here. It's hierarchical paths half. So we need to go to the test bench, AES encryption, and check the line 87 and 88. So here we've got the hierarchy. Maybe I will make it a little bit bigger. Here we've got the hierarchy. When we click on the test bench, AES encryption, and line 87, 88. Okay, let's go. It wants it designed in, so show source, entity model. Okay, so here's our entity. And we need to scroll down to the line 87 and 88. I missed something. Oh yes, here it is. So as we can see, it's primitive, but here's a bug line that we need to simply delete or comment, and we run the simulation to get rid of those X-rays reports. Because as you can see, to the Cipher text, 2 data was written at the same time. So the conclusion is that it achieves the X value, nor 1 or 0. When we run the simulation, I think we should run the macro. Run simulation. It will one more time get rid of the tests, 10 tests for the coverage results, and the simulation of the whole flow. Okay, so as you can see, there is no more X-rays report, so we can now discuss the whole flow simulation. On the simulation window, we've got 3 parts: the AES-ENC, that means AES encryption, the USB bridge. It shows us what exactly is going on the FMC, and the AES decryption part. It shows us what its execution on the hardware, on the TySOM. So first, let me 5 minutes. Okay, I need to speed up. So first, we've got encryption value here. So when the encryption down is from 1 to 0, we've got the encrypted cipher text, which then passed through the USB in special packages like T-data. It's the packages. So we can see there's 32 bits of data per each transaction. And after the validation of the data, so where the breached data is valid and decryption is valid, we then start the decryption process on TySOM. So when the TySOM receives all the data, it's starting the decryption. And after exactly 10 clock cycles, because the decryption takes 10 rounds, exactly after 10 clock cycles, we receive the data here, decryption done. And we can see that the decryption plaintext, it starts from 71.6e. It's exactly the encryption plaintext that we generated in the preconfig function. Okay, so that's the whole flow. One more thing that I want to show is Aldec coverage report. So here we've got the statement coverage, branch coverage, condition coverage, toggle, and path coverage also. And I really don't have the time to dig into the details, but just let me show you quick. When we hit our verification plan, the verification plan is the plan that we need to run through to get the report. And for example, when we see coverage for the statement coverage, we can see that's the 93%. And when we get to the links to get the details of it, we can see that most of the links are covered. But when we find something that marks on red, we can see that there are some problems. Maybe we can go there. And the problems are with SBox. SBox is our instance for coding. So when it receives 2 bytes, it encrypts them. So there is a logical way to explain the bugs, because we only need 32 bits 4 times. So 120 bits, so that's 16 bytes. And 16 bytes times 10 tests is only 160 possibilities. And there we have a lot more of possibilities to encrypt the data. So that's why some statements are not covered. With 100 tests, the statements coverage reaches about 99.8. I think that sums up our demo section, so we can exit the Riviera now. And we can back to the benefits and conclusions. I will try to make it faster. So the key benefits of this flow is flexibility. Let me show you. The key benefits of this flow is the flexibility. You can easily adapt your software. You can add some more function to it. The next one is scalability. You can add some hardware stuff or accelerator if needed. Early verification is the very important one. It supports your project validation from the start of it. Advanced debugs such as X-rays, coverage test planning that I mentioned, and logic profiler that it wasn't in my presentation, but it's also a very useful feature of Riviera-PRO. And real-time operation ensures fast, responsible processing, energy efficiency. The whole project is focused on the low power consumption, and modularity. easy to modify with custom hardware. I will skip this slide. This is those are some potential use cases that you can see after the presentation. So to conclude, this project demonstrates a flexible, scalable solution that supports early verification and real-time operation. In this project, we can see efficient workflow because VUnit automate, orchestrates, and simplify test execution. It has also a seamless integration. So VUnit, TySOM, and Riviera combine to deliver a complete testing flow. Hardware acceleration, we use TySOM to make the processor rest a bit. And advanced debug and verification in Riviera-PRO. So as you could see, the X-trace and test plan was giving us the powerful debugging and coverage analysis. Okay, so I think that that my part of the presentation is end. So now I would love to hear your thoughts or questions. Maybe do you have something? Yes, please.
Question. So if I understand it correctly, the encryption part was done in like Riviera, so it was a simulation of HDL, and then you jumped out into VUnit Python to do the actual communication over USB, right?
Mm-hmm. Yeah.
Okay.
Yeah. It was.
It's my understanding.
Okay. Anybody else? Okay. So thank you very much for.